Hi everyone. What you see going on the bench here with the meters operating here, all of these meters, is the verification process for this power transformer. And this is the power transformer that I'm going to use in this amplifier project. Now there are a lot of criteria that need to be considered before the purchase of a power transformer, or it could be a very costly mistake. And this criteria goes well beyond the electrical aspect of the transformer as well. And I'm going to share all of these thoughts and considerations with you in this video. So down the road, if you need to make a power transformer purchase, you can do that with confidence. Now, I haven't been very nice to this transformer. This transformer has been, I guess you could say, performance tested for quite some time now. And this is all part of that verification process. As I've mentioned many times here before, I will not release any information to any of you unless it's tried, tested, and proven. I want to make sure all the information that's released here is solid, and that's the reason that I have been testing this transformer so incredibly hard for the last little while. And now you're probably saying, well, what have you done to that transformer? Well, I'll start off with what's going on here and I'll lead into that. So first of all, you'll see a fan running down here and that's blowing on the load resistor here. So this resistor is mimicking what a speaker would be. So this is just what is known as a dummy load. And that's across the transformer. And that's just being powered up by these power supplies here. Actually, only the bottom power supply is operating the fan. So this fan will only draw air in through the front here and blow out this way. There is no draw on the other side of the fan, and for good reason. I don't want any draft around this transformer, and I don't want any air cooling around it. I want this transformer to only convection cool. For those of you that aren't familiar with convection cooling, that means when hot air or heat rises, it's going to draw cold air in from the bottom. That's called convection cooling. The transformer itself is stood off the bench by that little piece of aluminum there by about 1 centimeter to keep the core off of this mat, because the mat can act as insulation. I want this here to be stood off the mat so that air can freely circulate around the transformer so I can get a very accurate idea of how hot the core is going to get on this transformer. This transformer right now is powering this amplifier completely. So it's powering up the B+, which is the plate supply. It's powering the screen supply. It's creating a negative bias supply. And right now, it's also putting out the filament supply, so it's supplying current to both the filaments. Right now, it's putting out 10.4 watts, and it's clipping into that load right now. And here's the thing. It's been doing that now for 3 hours continuously, no breaks. It's been supplying 10.4 watts to that load in clipping for that amount of time. Now, here's the thing. The line voltage is directly reflected in the B+ voltage here, so there is some, I guess you could say, draw in the grid right now. Normally this sits up about 323 or 324 volts on the B+ side here. So this will change very quickly as the grid is moving around, and that just depends on the load, whoever's running air conditioners or, welder, furnace, whatever. Maybe stoves will draw this all down on the grid, and it's pulled it down quite a bit in the last little while. So this normally sits up about, say, 323, 324 volts, something like that. And right now it's down. It's still supplying, 10.4 watts into the load, which is doing okay. Now, variation on the plate is not a big deal. Variation on the screen is, and that's why I've built a regulated screen supply. And as you can see, it's very accurate and it doesn't move. It's sitting at 200.0 volts, and it's been like that for 3 hours. 200.0. So it's doing very, very well. Now, this was just a fluke. I really don't care if it's sitting at 201.6 or 198.2 or whatever. As long as it's close to 200 volts, it's A-okay for the screen. You don't want to really exceed anything beyond 200. Maybe 205 would be the max that I would want to put on the screen of the final tube or the output tube in this project. This little circuit here was released on Patreon quite some time ago, so I've already designed this and released this, and I'll talk more about this here in just a little bit. This is already created. This little regulator circuit is so simple, you can build it on a terminal tie strip, or if you like, you can build it on a circuit board, whatever, and it's very, very accurate. It works very well. Now, incredible accuracy for the screen grid in this amplifier is not important by any stretch of the imagination. If it moves around just a little bit, you know, maybe 199, 198 to 201, 202, absolutely fine, as long as it's right around the 200 volt range, and you know, it's going to regulate pretty well within that range, everything will be just fine. Normally when screens draw current in a power amplifier application and there is no regulation to them, it creates a lot of distortion. That's why the screen grid is regulated in a lot of power amplifiers, and this one here will be no exception. This amplifier will have a regulated screen and it'll sit at 200 volts, and this is very important to stop the tube from destructing as well. The tube screen has to be right around there. You can see there's 317 volts B plus, and that's being fed to the plates. Tube's absolutely fine with that. I've put 450 volts on the plate of this tube with this amount of screen grid voltage, and it's fine. There's no problems with it. All the tubes I've plugged into this fixture have stood out just fine, except for that one gassy one that you saw in the previous video there, where that tube was making all sorts of pretty looking colors. So anyways, lots of information to share here, and I've got a lot of stuff to share with you in this video here. So let's see, what else can I tell you here very quickly. Negative voltage on the control grid. This is the amount of current that's being drawn from the B plus supply right now. So almost 92 milliamps, and that excludes the bias supply. The bias supply is capacitively coupled into the secondary of the B plus here, so on the B plus winding, just because I'm running a full wave bridge rectifier and I can't use the bias taps. So this is a very interesting little circuit to create bias, and I'll explain that when I release the schematic to all of you, and I'll show you all the schematic. So kind of a neat little circuit there. So the bias current is not reflected in that whatsoever. Again, 3 hours at 10.4 watts, 10.5, something like that. It's moving around just a little bit. And that would be the equivalent to you taking, say you wanted to use this guitar amplifier and say put an electric guitar in it. Say you were to strum that electric guitar. That would be the equivalent of that electric guitar making the same sound at the same frequency for 3 hours without stopping, at the same amplitude or same volume level. Or say you wanted to use this little amplifier as a public address amplifier and you were going to put a mic on it and talk through it. This test would be the equivalent of you making the same noise into that microphone for 3 hours without stopping at the same amplitude and at the same frequency. So you'd be making a steady note. It's pretty impossible to do that. So as you can see, in normal application, when this is played, when you're playing a guitar, the amplitude is continually varying. The volume is moving up and down. And it's the same thing with if you were to use this for public address. If you're talking into a microphone or something like that, the amplitude is continually varying. And of course, the frequency is varying as well because your voice is, you know, the tone is changing of your voice. So there's a frequency variation there as well. So you could look at this as a very extreme test to this amplifier. Now the amplifier will go beyond this. It'll go to about 13 or 14 watts into full clipping. So you'll see crossover distortion here and everything. But this is, you know, beyond 3/4 of the way this amplifier would work in a continuous application. And that is a really good performance test for this transformer. The transformer, the power transformer, and the audio transformer get warm to hot. So when I say that, I'm talking about 45 to 50 degrees C is what these transformers are getting to. And it's staying there. Now, depending on the line voltage, I know the line voltage is soft right now because of what's happening. You know, the transformer may get a little bit hotter than that, you know, under full load like this for an extended period of time. But where is this going to happen unless this is purposely done? Again, this is, you know, kind of a torture test for this transformer. I'm being a little bit nasty to it right now. Now, another thing I'm going to tell you about, I don't suggest that you do a setup like this. This is my own verification process for this power transformer, and this was put together very fast so that I could verify this because it took a while to choose a transformer, to verify it, test it, do all this stuff, and then to receive it via shipping and all that kind of stuff. And I'm basically here right now. That's how long this has taken in the process. This was put together very, very quick. The test procedure was put together very quick. So everything else in the search criteria and everything to get this transformer here wasn't that incredibly quick. So I'm hoping by the next video that I'll have this mounted to the chassis with the power transformer, the tubes on it, and I'll have this thing very close to working at that point. It's getting close now. And I can tell you that after this video, the filming is done with this, or the videoing is done with this video here, I'll be drilling holes in that chassis right away. So that's how eager I am to get this project on the move. I'm excited to get the final project done. Now, again, if you're following along and you're doing anything like this, you're doing so at your own risk. Be very, very careful, because this transformer creates high voltage, as you can see. Now, this is the loaded voltage right now with a sagging kind of line voltage. Normally 324, something like that. Now, here's the thing. This is loaded right now. Okay, as you can see, it's putting out 10.4 watts into distortion, and this transformer is probably not very happy with me right now. But when you first turn the amplifier on, so the tubes are all cold and everything, the B plus voltage is around 380 to 390 volts. That's with no load. As the amplifier warms up and the amplifier starts to draw 30 milliamps, that's where I've set this for. So this is the bias voltage right now, and that'll give me a bias of about 30 milliamps here with no audio going into this at all. This will sit at about 30 milliamps. When this sits at 30 milliamps, this will sit at about 350 to 355 volts. When you turn this up, when you turn your audio generator up to create about 10.4 watts output, that is the drop. So it drops down to about 317 to 324, 325, we'll say, just to round it off to something even, 325, something like that. Now this here, this transformer in the criteria, this is a multi-tapped transformer, so there's a lot of taps on this, and I'm going to talk about that. And the reason that I spent the extra time is because I want this so that it doesn't only favor people in North America, so that this transformer favors everybody in Europe as well. So I want this to be as universal as possible for any of you that want to create this project. So lots and lots of stuff to talk about here. So what I'm going to do is I'm going to move this all out of the way now, because this is verified. This has been running for a long time. That's only 3 hours in one stint. Okay, so this has been running 3 hours in one stint, 2 hours in another stint, 2.5 in another stint, all just to make sure everything is operating correctly. And everything is, I say this little Hammond transformer is working very well. It's a great little transformer, so this would be perfect for this project. This is the power transformer that I've chosen for this project, and it's a Hammond 369AX. It's still nice and warm from the testing. Now, there were a lot of considerations before I ordered this transformer. One is size and weight. Got to remember that that little chassis is hanging upside down in that cabinet, and these things are pretty heavy. The chassis really isn't all that big, so I don't want this to be too incredibly heavy. That worked out very, very well because of the current that needs to be supplied to the load, so that worked out okay. Another thing that was really nice is you can see the feet here. They've got a bit of a space between the core and the bottom. Now, on the actual amplifier chassis itself, this transformer will have to remain in here to power this up because there are no taps on this new transformer to make that happen. And whenever you're ordering a transformer nowadays, especially one like this, that's intended for vacuum tube use, you are a little bit limited. You wouldn't have that, say, 14014 or whatever it is on this one here. Yes, it's 14 times 2, right? So 14014. You wouldn't have that in a transformer like this, right? But anyways, back to this. You can see this space here between the core and the foot, which is very nice because when this is mounted, you can see these screws will go right underneath the transformer just like that. So these screws can be left in place. Now, this transformer will end up sitting on this chassis just like so. So it'll be sitting over here like this. Of course, holes drilled for the wires to run inside. It'll be sitting over here. And provisions will have to be made, so I'll slip the chassis back into the actual cabinet itself, and I want to make sure that the transformer is far enough away from the wooden wall so there isn't any interference when this is taken out or put back in. So this will be a fair ways away. And then the audio output transformer will sit over here like so. So it'll sit on this end. Now, if you're going to try and jump ahead of me and put this whole thing together, make sure that you do not mount your transformer like this, because they will couple. You want the transformers like this. There is a bit of space between them, but there still is a chance that, these will couple and hum if you have them like this. So you want to keep these in this here. And again, with thought consideration between the wall, the actual wooden wall of the cabinet, and this. So you want this in a ways so that this doesn't interfere with the cabinet at all. And then there's a lot of room in the center here to mount those two tubes. Lots of space on the underside of the chassis. While it's on my mind, I'm going to also mention in this amp here, so this TDA 2030 is going to go missing, so this will get removed, but I'm going to leave the heatsink in because the pass element for the screen supply, the 200 supply, is going to screw to this side of the sink. So this sink will be the heatsink for that, and that works out very well. I can leave this in, use it to hold the board, and it's the heatsink for the screen supply. So that worked out very, very well. I'm glad I didn't remove this already. So with me, it's one step at a time and work towards the end here. So I'll just move this out of the way, move the transformer back into the shot. So now you can see here, using this, you can figure out the rough dimensions of what's going on here. So you can get an idea, well, I shouldn't say rough, very close dimensions of the transformer that you're going to be ordering. And that, of course, was part of that criteria. Now, this has to be friendly for all of us here in North America, and it also has to be friendly for all of you in Europe. And that's the reason that I ordered this series, because it has multi-taps on the primary side here. So this will work for North American and for European, right? The power system in either area should be just fine. Now you can see on this side, if you were to run the red-yellow to a center tap and you would use 125, 0, 125, you're not going to end up with a whole lot of B+. So you have to go end to end. You're probably saying to yourself, well, why didn't you just go with a different type of transformer? Well, the whole thing is size consideration, the amount of current available, and not only that, you're dealing with weight, the weight on the chassis, and the selection of transformers. There is quite a big jump in the selection if you actually look at the series of transformers. And of course, the size, with more current gets bigger because that's how transformers work, right? So this seemed to be a nice balance for everything, the size and what's here. So what I come up with is I go end to end. So there's a bridge rectifier on here, just like this one right here. This is the one that I used in the testing, a little bleeder resistor across the cap to drain this off. And this is just my test rectifier. So end to end across this, but now for the biasing, it really just eliminates these two taps. There's no point in using these. So basically you're capacitively coupling to one end of this and then running a diode off a capacitor. And I'll show that to you in the final schematic. And that's how you create a bias supply when you've basically used up the winding with a full wave rectifier. So that worked out quite well. So it's a 6.3 volt center tapped filament line on this, so nice balanced system. So the center tap would obviously go to the chassis. Now, if for some reason I find that running AC on the filaments is noisy in this application, I'll rectify it and drop it. That is yet to be discovered when this is all put together in that amplifier chassis, and that will be available on the schematic. So 2 amps is absolutely fine for this. And as you can see, 3 hours of operation at pretty much, into clipping at this point, and the transformer is warm to hot. It's working very, very well. So I'm very happy with the performance of this little transformer. Now you're probably looking at this output transformer and going, the output transformer is huge. And yeah, it is huge. But again, this allows for a lot of different application. If you wanted to build another type of amplifier, you don't need to use this transformer. You can use this for many different types of applications. It's a very versatile transformer, even with the plate-to-plate impedance on this other side here. It's a great transformer. So this one here is big, and again, to get the correct impedance and then to make it work with that tube that we're using, there wasn't a whole lot more options than this one here. There really wasn't. It would have preferred, I would imagine, a 10,000 plate to plate, the impedance, 10,000 plate to plate. But 84 was about where it was, and then of course rated at about 18 watts, right? So there's a lot of room to spare. So that just worked out very well. Yeah, the transformer is a little bit big, but very resilient. And it gets up to, pretty good temperature too under full load for a long period of time. And that's just due to the massive amount of windings inside there to make, 8,400 ohms. So, and all that stuff, right? So, very nice transformer. Oh, and one question I get about these transformers a lot is this black stuff that they've coated it with. Basically, what they've done is they've dipped the transformer. If it chips off, is it okay? Yeah, it's absolutely fine. So this one here is a chipped corner. I'm not too worried about it. I have a few of these transformers. I ordered up a few of them because I've got some other ideas planned for here as well. And this is a very nice transformer. So, it's been dipped and it might not look all that pretty, but performance-wise, it's quite pretty. Anyways, I'll get into that in a future video. So, as you can see, it's coming off the wires here already on this stuff. So this black stuff just comes off absolutely fine. Not a big deal. You see some of it's on here as well. I think this might just be paint from them painting the transformer though. At any rate, so everything seemed to work out. There's a lot of things to, that were taken into consideration. And they have a transformer that's very similar to this with just basically one winding on it. And of course, that wouldn't work for all of you in Europe. So I wanted to make sure everything was just as friendly as possible. Keep things as versatile as possible. And this transformer just happened to work out that way. So between the spacing on the bottom for the screws and the taps and the size and the weight of the actual transformer, because it has to be hanging. You got to remember that this thing is like so, right? And this thing is hanging on the bottom side of that chassis. And this is held up by basically 4 screws, right? Here, 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 and here. So with this transformer on it and this transformer on it, you're dealing with quite a bit of weight. And you got some inverted tubes and the rest of the associated circuitry inside. So that is the way it goes. And that's basically just the idea that I use. Now, here's another thing that you want to keep in mind. Something that really isn't talked about a whole lot. Didn't mention this. So you can see here, secondary rated voltage is under load. So this is under load here, but you can see here secondary no load voltage, NLV, that's what that stands for. You can see 270.4. All right, red to red, so that's end to end. Okay. So now, you know how I said it would be about 385 or 380 volts, right? So let's see how close that is. Very easy to do this. So this would be the no load DC voltage that we're going to be looking up right here. So all you do is you can take that 270. So we'll turn this on here. So you go, this is 270.4, positive or negative 2%. So we'll say 270.4. We'll just use that anyways, okay? And of course, this will vary with the line voltage as well. If you have a strong line voltage, you see there's 120 volt taps. If it's 125, sometimes they're 127 in some places, you can expect this to go quite a bit higher. So that's all things you need to keep in mind. That's why choosing transformers gets just a little bit tricky sometimes, right? Especially if you're looking for a very tight area that you want the transformer to operate in. Okay, so 270.4. So you go 270.4 times 1.4. And that'll give you what you're going to be having, at the rectifier output. So, at the output of the bridge rectifier with no load. So that would be this capacitor charging right up. Right, this has a little bit of a bleeder across it, 390 ohms, something like that. But at any rate, that's what this would be seeing. So a no load voltage. So you wouldn't just normally think that, right? 270.4 AC turns into 378.56. You got to remember that this thing is basically turning into a peak detector with no load, right? Minus the drop of the diodes and things like that. So you could factor in the drop of the diodes in the rectifier, but it's so minimal at this point, who really cares? I know people like to do that. They'll do this and then they'll, take away the drop across both the diodes that are switching in the rectifier. What's the point? You're dealing with, this kind of voltage that's nothing. So, what are you dealing with? 0.6 on each rectifier, so 1.2 volts, as it's switching back and forth, right? So, not even worth factoring in. At any rate, 378.56 is what you're going to see free with no load. So this was about 380 to 385, so very close to this, right? Very close. And then, of course, when this was loaded with about 30 milliamps on the DC side, it came down to about 355, 350, something like that. And then as you saw under full load, down to about 325 to, with a sagging line that I had here, I think it was 317 or something like that. So all things that you need to factor in there. Now, again, if I find any hum in there, I'll be taking this and rectifying it through another bridge rectifier for the actual tubes themselves, and I'll get that again. So once I get that raised, what I'll do is, you put a capacitor and a dropping resistor across it, and then another big capacitor, and you get a very clean DC supply to the filaments of the tubes if there's any hum. So that works out very well. So any way I look at it, I'm not worried about it. If it works well with the center tap to ground and a balance system, no problems. If not, I'll rectify it. And I'll share all that with you as well. So a few things to keep in mind whenever you're designing things here. 1.4 is close enough. You don't need to really be going out any further than that. That'll get you into the area of, where you need to be. And there you have it. So that is the power transformer, and this will be on that chassis by the next video. And so will that output transformer. And I'm hoping that I actually have something that's completely running, and then I can explain it all, share the schematics and all that in the next video. So I'm very excited about this. Everything so far is working out incredibly well with this project. Things are just falling into place like they should, and I'm very happy with that. When things start out like that in a project, you're in for a pretty good result. So there you have it. What else can I tell you? In the schematic, in the end, I'll show you all the wiring and all this on this transformer. I'll edit something like this into the schematic and show you how to wire things up for the different situations. So like in my situation right now, quickly, it's white and brown are attached together because I'm putting both of these windings in parallel. So white and brown are together, and then we have black and blue together. So if you look here, you can see the black and the blue wire are tied together, and the white and the brown are tied together. And then those are the two lines that run off to the AC for the testing. These are just all insulated. I slip a really tight piece of heat shrink tubing over these when I'm doing the testing. Now, not really suggested, but if you wanted to up the voltage just a little bit, instead of running at the 120 volt tap, you could run at the 110 volt tap, but everything will go up really high on this side. And of course, the transformer will get a little bit hotter as well. So there are a few things that can be done, but if you have, say, a 115 volt line, something like that, and it's kind of a toss-up between the two. So it just depends if you want to have less voltage or more voltage, right? Things like that. Things to keep in mind, 117 volts, things like that. And then, of course, this is also friendly for Japan as well. 100 volts and 100 volts works out well. This is the regulator circuit that I'm using for the screen supply in this amplifier. This is available in video number 39. So if you go down the videos list, click on video 39, you'll get all the information, and you can watch a video about this particular regulator circuit. There are other regulator circuits in there as well, a vacuum tube one, and this one here designed around a transistor as well. Now there's a big bonus in using a FET. The FET itself is a voltage driven device, whereas transistors are current driven devices. So obviously if this has to, be attached to a current driven device, this has to supply current to that device, whereas a FET has that advantage of being the voltage driven device, and that's why I prefer using FETs in this circuit here. Now, this is a different FET. This is the one that I originally used in the design. This is the one that I will be using in this design. And as you can see, it's a completely isolated case. So this can screw directly to the heatsink without any spacer behind it. So I can put heatsink compound on here and or I should say thermal compound on there, and just screw this to the heatsink. These FPAC style FETs are very, very nice for that. So the number of this device is an STF4N90K5. That's the part number of this device that I'm going to be using. Now, again, this thing is very, very versatile, and, this FET here is very tough. This would be absolutely fine to use this FET in here, but this is, I guess you could say a little bit smaller and just a nicer device for the job, that's all. So with that small heatsink on it that you saw on the board off to the side in the original test, it gets pretty warm, but with a large heatsink like what you see in the actual audio amplifier itself, it'll be absolutely fine. And of course, with the TDA 2030 missing on the other side, that sink is just, again, it's just acting as a spacer for the board, and it's just kind of like a wall there, so why not use it as a sink from the other side? That just worked out very, very well. Now, when you put this together, be very cautious to follow this exact schematic. So make sure that you do put the Zener diode in there. And in a case like this, put this diode across the source to drain. Make sure it is the correct way as well. Just a couple of safety precautions. I talk about this in that video, why that's needed. Now the math is here to work out the, to work out the screen grid voltage. Now I'll tell you, it gets you close, but not right on top. Different devices act differently in the circuit. So what I found is 330 k ohms, so a 330k and a 6.2 k ohm resistor gave me 200.0 volts. Now, of course, one could add a trimmer underneath that. You could use you could probably use that 330k and then put a 10k trimmer on the bottom end of it. And then you could, vary it either side if you want, just a little bit. So with 330, it's a little bit low. And then when you put the 6.2, it bumps it right up to 200. That worked out very, very well. So at any rate, would be the resistance values that you would choose down here to make this circuit, give you 200 out instead of 300. And as you can see, it's very stable. It didn't move for 3 hours. Now, mind you, from no load to full load, you will get a bit of variation there just because of where you're going to be reading the voltage and, of course, other things in the circuit. But not a big deal. The slight variation that is there is absolutely fine. As I say, if it even if it was at 202 volts, and then when you loaded it, it went down to 200, it would be absolutely fine. Not a big deal. It doesn't have to be that incredibly crucial for a circuit like this. But as you can see, this is very accurate. So it just depends on the device that you choose and everything. Again, very versatile. This is just what I'm going to use. I have a bunch of these on hand, as you can see, and they just work very, very well. So definitely check this video out as well. Nice regulator circuit. There's 2 other regulator circuits there as well that you'll find very interesting. The one with the vacuum tube is surprisingly good. I spent a lot of time with that one vacuum tube designing a regulator circuit and a transmitter that I designed quite some time ago. The vacuum tube is astounding. The stability is just astounding. Voltage dropping on the input, current being drawn on the output at the same time, and it stayed rock stable. It was, just movement everywhere, and that regulator just held up. I was very impressed with that tube. So definitely check that out as well. Definitely check that the vacuum tube circuit out. So anyways, there you have it. So hopefully by the next video, I should have pretty much a completed amplifier. I'm very excited to get this done, and I'll share all of this information with you in the next video, and we'll go through and do some testing, and I'll show you some signals in different places and things like that. So it's coming along very well. So if you're enjoying these videos, you can let me know by tapping the heart symbol below, and I will talk to you all very soon. So bye for now.